Hi everyone, I am Shaumindu Kumar Ghosh. So I am an AI research intern in the Advanced Architecture Research Group in the Client Computing Group Business Unit in Intel. I am also a SRC research scholar in Purdue University. And this work, which is enabling sustainable AI using energy efficient intelligent system, is done in collaboration with Arnab Raha from Intel and Vijay Raghunathan from Purdue University, and it's sponsored by CBRIC and SRC. So what is deep learning at the edge? So deep learning deals with using or running AI models on different edge or end user devices. And its applications can range from smart city, autonomous driving, smart homes, virtual reality, speech recognition. Many of you are already aware and have been using AI in your day-to-day lives. For example, in Alexa, you are using speech recognition. For playing games, some of you might be using virtual reality. And in your homes, there might be some smart thermostat managing your temperature. That is an example of smart homes. And also when you are opening or unlocking your phone using your face, that's an example of face recognition, which is also an AI application. Now, all of these deep learning or AI models are running on these very low power devices and which are powered by battery. So that's the thing we are calling the deep learning at the edge. Energy efficiency in DNA inference is perhaps the most important requirement in today's edge devices. Now, although DNNs, that is deep neural networks, which are frequently matching and exceeding human accuracy levels for these applications which I just told, it comes with different challenges like high computational complexity, also high energy consumption. However, all these smart devices which I talked about, they are very constrained. And by constrained, I mean they have very less compute and memory as well as very limited battery life. So to have a path to a sustainable and green edge AI, we need extreme energy efficiency in DNN inference. DNN inference algorithms that are used for performing various visual analytics applications like face recognition, object detection, image segmentation, these are typically error resilient. And this resiliency actually comes due to DNN's ability to work with noisy inputs, due to information redundancy, their self-healing nature, as well as their ability to be resilient to approximations in their computation. Now, one important thing is approximate computing is a technique which can leverage any application resilience to give you energy benefits. So that's a very good technique which many people use and have been using for a long time. And this approximate computing we are looking into in this work. Now, if you look at a snapshot of different works in this area, most of the work on DNN approximation, they target the compute or the processor of any device, any electronic device. However, in a typical embedded system, for example, a smart camera, computation is only one component of the entire system. In order to fully leverage DNN error resiliency and extract the maximum energy efficiency, we need to explore how to approximate the entire system, not just the compute part. Now, if you take an example of a smart camera that is used for object detection, so if you dissect such a device, you will see it consists of compute, that is the processor, its sensor, the memory, then there is a communication module. So it turns out that all of these subsystems contribute a significant portion to the energy. Therefore, if we want to maximize the energy benefits, it is important to focus not only on the compute part, but on all of the subsystems. So this is our idea or this is our goal, where we shift our focus from approximate computing to approximate inference systems. So what are our main contributions? So this is the first and only work to propose an approximate inference system or axis for energy efficient inference at the edge. So in this work, we have introduced approximation in different subsystems. We have also designed two separate variants of axis called CAMEdge and CAMCloud. And we also have developed a prototype of this axis system and have run different types of applications like classification, detection, and segmentation. And experimentally, we have obtained close to like 4x, up to 4x energy savings. So this slide shows different types of approximation for different subsystem. So on the left hand side, you can see the sensor subsystem is approximated using nearest neighbor subsampling, which basically skips some pixels to give you a lower resolution image. Then in memory, we are using refresh rate reduction, which is another approximation technique for memory subsystem or on which is used on the DRAM. For the compute part, we are actually using structured pruning, which is a very popular technique to reduce or to compress these large DNN models so that they can run faster and in less energy. And finally, in the communication subsystem, we are using JPEG compression, which basically compresses your image before it is offloaded to some cloud server. Now we have individual approximation knobs and a specific quality bound of 5%. Now we modulate the approximation levels of each subsystem and conduct quality energy sensitivity analysis to measure the overall system quality and energy. Now we select the approximation configuration with the maximum energy quality gradient to update the state for the next round. That you can see from the star location on this image. Now in the next round, we continue the exploration from the current state and eliminate the subsystem which violates the quality bound. Now this iterative pruning process is continued until no subsystem can be approximated further and the corresponding energy and quality is your final values and that is saved. So in this slide, you can see our experimental prototype, which we have implemented on a Intel FPGA board. It has a Micron 5 megapixel sensor. It has a 1 GB DDR DRAM. It has the NIAS soft processor core, as well as the communication module. And on this particular prototype, we have evaluated 14 different neural networks, deep neural networks, to evaluate the performance of axis. And as I mentioned, we are using 3 different types of application, that is image classification, object detection, and segmentation. This slide shows the comparison of axis with individual approximations. Now, if you see on the left-hand side, this graph is for CAM edge. The x-axis represents the quality loss bound, that is how much quality loss the user can tolerate, and the y-axis shows the normalized system energy, that is normalized to an accurate system where no approximation is there. So if you see from the columns, you can clearly see that axis gives you the best energy savings compared to approximating any other individual subsystem. So the line graph shows the energy savings where you approximate only one subsystem. Similarly, on the right hand side, for CAM cloud version of our axis, you can again see that the axis represented by the columns that represents the best energy savings compared to the other subsystem approximations. Now, overall, across a quality loss bound of 0.5 to 10%, you can see the comparison between axis and the different subsystem approximation in the bottom part of the slide. So hence we can conclude that synergistic approximations in axis achieves better energy efficiency than individual approximations. That is the key idea which we are trying to put out, that you want to approximate or optimize all the subsystems of any embedded system or any device that will give you the best energy efficiency. Now that we have looked into the approximate inference system, let's look at the landscape of approximations for DNNs. From there, I will tell you what I am doing currently at Intel. Now, if you look at the compute and memory approximations, there can be hardware approximations. There are algorithmic approximations which approximate the DNN algorithm itself. There is software approximations where you directly modify the software only. Another kind is the hardware software co-approximations, which actually gives you the best bang for the buck. Now in hardware software co-approximation, quantization is a very popular technique which is used to reduce the DNN model size and give you some benefits. Similarly, can be different approximations in the memory, for example, voltage scaling in SRAM or refresh reduction in DRAM. In the Advanced Architecture Research Group at Intel AI, we are trying to enable energy efficient AI using approximations. So we are currently exploring the impact of different approximations on DNN performance. For example, quantization, which reduces the bit precision of any DNN model while maintaining your accuracy. And this quantization can lead up to 4x reduction in model size. Now we are implementing similar kinds of approximations, compute and memory approximations in AI hardware and software design. This leads to speed up of inference latency and increase the energy efficiency of the AI hardware. So this facilitates Intel's mission to bring low power and intelligent and AI ready client systems to masses. Thank you for listening to this talk. So the key takeaway of this talk is these concepts of the very first approximate intelligence system will empower you to build energy efficient and smart systems, and that will allow you to make AI available to each and every person in the world, so you can truly make an impact in the world. And these are some of the references, or these are some of the papers which talks more about this work.